another client approached us at first to complete a traditional survey of the superstructure that would support multiple wrappings of tubular HSS steel for each floor of a new building being constructed at the Edmonton Airport. Timelines for this survey were extremely short, and we had many other factors to consider. The idea was that the HSS steel would flow up and down and in and out around the building and would be used to affix a truss system that would eventually support channels supporting a unique zinc cladding. The building was to fit naturally within the high grass and blowing snow of the surrounding prairie fields. Here's a look at how the truss system connects. There were 1,000 trusses that would eventually hold the cladding. Each one was different. These are the truss anchors, and these are the steel window rails. So literally every floor had 4 of these. Here you can see windows above and below the truss system, as we just saw in the SketchUp. The designer wanted a survey of every HSS steel joint and every knife plate. All in all, this amounted to approximately 8,000 survey points. While reflectorless technology existed within our fleet of 1-second total stations, we felt it would be difficult to ensure that the sighting of these joints and plates would be achievable from the distances and the angle of incidence. Moreover, we were working from an active tarmac, so we had very time-restricted windows for instrument setup on areas around the building. We made the argument that point cloud capture would achieve the completeness that we needed and would also achieve the accuracy. This was our initial scan of the building using a time-of-flight C10 laser scanner. We imported the designer's 3D model directly into Cyclone. And we were able to compare the design to the as-built. This proved to be extremely valuable, and it garnered confidence from the engineers and architects working on the project. There's a picture of the scanned trusses. Working with the designer in New York, we virtually surveyed the lower edge of the steel and placed vertices at the joints and knife plates. This was all delivered in a format that could be imported into the designer's in-house software. This was just one example here of differences we found between the design and as constructed window rails. You can see here the orange is the as-built, and then this is the model. And I think this is the largest discrepancy we found, and it was 334 millimeters, or just over a foot. So certainly that would have created some issues for the truss building. If the contractor had been required to measure and fabricate on site, like was the original plan, the project would have been behind schedule and likely hundreds of thousands of dollars over budget. The original process was to build the trusses off the design, but since there was so many differences between design and as-built, that would have definitely created a budget problem. So that's kind of the that's a view of the building is now finished. Of course, this was back when they were just completing it. And it's just that's a building looking east. You can see how the zinc cladding was put on and how it looks wavy like snowbanks. Anyway, this project garnered us a front page on an industry trade magazine, so I just wanted to put that up. And I stole this quote from Brendan's book, and I think it made, I think it certainly made a lot of sense that, the degree of variability they had to build into the truss mounted brackets would have been impossible had we not gone out and been able to give them as-built data and quickly, so that they could deliver those trusses. And I don't know if I mentioned it, I might have had it in one slide, but out of the 1,000 trusses, they only had to rework one, and that's because they dropped it off of the Fracco tower.